So we are going to learn today what tautomerism is and what are the types of tautomerism we can see in various types of molecules. What is a tautomerism actually? If there is any alpha hydrogen in a molecule, then the position of the alpha hydrogen wherever it may be possible with the help of a conjugated double bond, if shifts from one atom to another atom, then it's called actually tautomerism. It's like simply if we consider a structure like this, if this alpha hydrogen gets promoted to the oxygen atom, then we see here this is, and the double bond shifts from this area to this area, and the proton shifts from this area to this area. Now what the basic facts we notice here is the hydrogen must be, H atom must be in alpha position with respect to a double bond. That is, H atom is in conjugation with the double bond. The next most important thing is that the hydrogen atom gets shifted from one atom to another. So if we consider that fact, the hydrogen atom is gets shifting from one to another, so which the atom which takes the hydrogen atom must be basic in nature. So this phenomenon solely happens where there is an atom attached with the double bond is basic in nature and must be strongly basic in nature. If the atom is not strongly basic, then it cannot take the hydrogen atom towards itself. Basically তাহলে আমরা কি বলতে পারি, যদি একটা হাইড্রোজেন অ্যাটম আলফা পজিশনে থাকে উইথ রেসপেক্ট টু দ্য ডাবল বন্ড এবং ওই ডাবল বন্ডটার সঙ্গে অ্যাটাচড অবস্থায় যদি কোনো বেসিক অ্যাটম থাকে, তাহলে দেখা যায় যে ওই আলফা হাইড্রোজেন অ্যাটমটা নিজের পজিশন থেকে সরে গিয়ে শিফট হবে টু দ্য বেসিক অ্যাটম। এই যে টোটাল ফেনোমেনাটা, এই ফেনোমেনাটাকে বলা হচ্ছে কি টটোমেরিজম। And depending upon various atoms and molecules, they can be classified into total 6 categories. First, keto enol tautomerism. What is keto enol tautomerism? When the phenomenon occurs in a ketone. Let's say here this is acetone. Now this gets shifted towards this one. Here the structure will be like this. But as per equilibrium study, we see that mostly the equilibrium lies towards the left, because this is more stable structure than this one. Now when we talk about a ketone like this one, that is a diketone. The form will be like this. Here we will see an intramolecular hydrogen bonding, this one. Intramolecular hydrogen bonding makes it stabler than this type of structure. So that's why for this type of example we see enol form nearly about 3.98%, but in this case we see nearly about 18% of enol form. And why this is called enol? There is an in structure and there is an ol structure. That is why it is called enol, as enol. Now this enol contains an intramolecular hydrogen bonding. That's why for this type of molecule where we get an activated alpha hydrogen, then we get the enol form, existence of enol form in higher percentage, but the equilibrium shift towards the left always higher. Now second type of tautomerism is Ketophenol tautomerism. Ketophenol tautomerism. This must be a cyclic ketone which is alpha beta unsaturated and as well as gamma delta unsaturated. Now for this type of ketone we see here true hydrogen and this one gets here shifted. Now the structure will be like this, and as we see here, after getting the enol form, I mean actually phenol form, it is more stabilized by resonance, even including the lone pair of the oxygen in resonance. This structure is much stable than this one. Thus, for this type of tautomerism, the equilibrium lies towards right position, and the phenol form has higher stability and it is in higher percentage in the medium. Now, nitrosooxy. For nitrosooxy, we see the structure is like this. Let us say like this. This one will get promoted to this oxygen atom, and the equilibrium will lie towards the right. The structure will be like this. One lone pair and OH. As this is more stable in structure because the oxygen with its lone pair can involve resonating structure here, the equilibrium will be in favor of the oxime form. This is called oxime and this is called nitroso. So the equilibrium will shifted much more higher in oxime form. Now the fourth one is Nitroac tautomerism. Nitroac. And if we pronunciate this structure as nitro and Ac, then we can easily predict that this tautomerism is between a nitro form and a acid form. How? For a nitrogen structure, the structure is like this. It is nitro. Now here we call this one, let's say type of this. So the tautomerism will be like here and here. Now the structure will be like RCR double bond N OH minus. Now easily we can assume that this structure is much less stable than this one. For what? Because here this oxygen can incorporate resonance with this one like this, but it will always be continued as much time as it is in this form. But for this one, that much resonance stabilization is not happening. Why? If we see the resonance structure here, then it will get like this one, which is actually very less stable due to this fact. Now this is unstable structure and this resonance is not happily to make this resonating structure. That is why in this case the equilibrium always lies toward left, and this is much stable form than this one. Okay. The fifth one is imine-enamine tautomerism. Now what is imine-enamine tautomerism? Imine-enamine. What is an imine structure? An imine structure is like that. But the structure is like this, or even there can be hydrogen or alkyl group, whatever it is. But if we see this, now if we see this, there is one hydrogen atom here, one hydrogen atom here. It may be also alkyl group. But which one is the alpha hydrogen with respect to the double bond? This one is the, with respect to the double bond, this one is the alpha hydrogen. So it will get shifted to this one. Now we see the structure as R C R double bond C. It may be hydrogen or alkyl group, whatever it is, like this. Now in this case, this is a much stable form than this one when nitrogen is bound to an alkylic group. If it has a hydrogen attached to this one from the very first, then the left structure will be more stable. What I meant to say is, like, if the structure was like this one, then the proton shift would have occurred like this and the structure would have been like this one. Now between these two, this is much stable, but not this one, this is less stable. That is why, because of the incorporation of the lone pair of nitrogen is much more available for this one NHR, but much less available for NH2 for incorporation into resonance of the lone pair aciding in nitrogen. Now, this is the reason, if the nitrogen has no hydrogen atom attached with, then the equilibrium will shift towards right, and if there is hydrogen attached to the nitrogen atom from the very beginning, then the equilibrium will lie towards left. This is imine-enamine tautomerism. And the sixth one and last one, that is called valence tautomerism, where there occurs shifting of intramolecular bonding position, not any hydrogen position. It mainly occurs in polycyclic compounds. Like if we see the example of Valence. This is a structure of valvaline as like this one. Now, here one bond will shift from one position to another, and thus it will be like this. This one will get into this one will get into this, and this one, sorry, there is a mistake in the structure. And this one will get into this. Thus the structure will be like again there was a mistake in structure. This, it has been here, and this is here. Now we see there is a 3-3 sigmatropic shift. What is 3-3? From this bond 1, 2, 3, from this bond 1, 2 and 3. 1, 2 and 3. Now this is 3-3 sigmatropic shift of bonding from one position to one position. There is no shifting of any hydrogen atom, rather there will a shifting of a sigma bond will occur in polycyclic compounds for continuous rearrangement of their structure. This is called valence tautomerism. Mainly this occurs in polycyclic compounds. So this was all about tautomerism we need to know, and those examples and classifications where we see various type of tautomerism. Thank you.